We present our work in this video, Frequency Domain-Based Diffusion Model for Unpaired Image Dehazing. Recent deep learning-based methods focus mainly on developing supervised models using synthetic paired hazy and clear data. However, acquiring paired hazy clear data is prohibitively expensive and time-consuming. To tackle these problems, an increasing number of unpaired image dehazing methods have emerged. This method learns useful knowledge for haze removal directly from unpaired input data, more practical and promising. Therefore, this paper investigates unpaired image dehazing task. It aims to use unpaired hazy clear data to train models for recovering haze-free images, and can be applied to improve the performance of subsequent high-level vision tasks. This work is motivated by the unique frequency domain property that the illuminance contrast is manifested by the amplitude spectrum. This means that the haze degradation is mainly manifested in the amplitude spectrum. If we can reconstruct the amplitude spectrum of a clear image, we can remove the haze degradation from the image. In addition, the diffusion models have shown impressive performance in image synthesis and detailed restoration tasks, providing inspiration for reconstructing amplitude spectrum of clear images. Therefore, the main challenge of this work is how to make diffusion model learn the haze-related amplitude of a clear image in unpaired training setting. Our contributions are summarized as follows. First, we propose a novel frequency domain-based diffusion model for unpaired image dehazing, called FRDiff, which is the first study to integrate a diffusion model into unpaired restoration tasks. FRDiff enhances haze removal capabilities by learning amplitude reconstruction from unpaired data, providing inspiration for other unpaired restoration tasks. Second, we propose an amplitude residual encoder, called R, that generates amplitude residuals to bridge the gaps between hazy and clear domains without adding extra parameters, providing supervision for diffusion model training. Third, we propose a phase correction module, called PCM, designed to eliminate unwanted artifacts by refining the phase spectrum using an attention mechanism. Finally, extensive experiments show that FRDiff outperforms existing SOTA methods with fewer parameters and flops. This is the framework of our method. Our FRDiff includes a dehazing network and a diffusion model. Diffusion model is employed to reconstruct the amplitude residuals, which represent the amplitude distribution gaps between the hazy and clear images. Meanwhile, dehaze network is used to fully utilize the reconstructed amplitude residuals. At each scale of the dehazing network, we introduce a frequency compensation layer, called FCL, that utilizes the diffusion model's output to refine the frequency features. The core of FRDiff is to integrate the diffusion model into the frequency dehazing process, so that diffusion model learns useful knowledge from unpaired input and guides the dehazing network. Our method adopts a two-stage training strategy. In this stage, we aim to train a robust frequency domain dehazing network by exploiting the amplitude residual extracted from the unpaired input images. We utilize the proposed amplitude residual encoder, called R, to obtain amplitude residual Z, and train the dehazing network for haze removal. R can obtain an amplitude residual that compensates for the gap in distribution between hazy and clear images without altering the texture structures present in the hazy input. We found that severe haze can obscure the texture structure, resulting in unrealistic textures in the dehazed results. So we also use the proposed phase correction module, called PCM, to further correct the slight differences in the phase spectrum before and after dehazing. In this stage, we aim to train diffusion to learn the reconstruction of amplitude residual from Gaussian noise, which enhances the capability of the dehazing network. It consists of a diffusion process that adds noise to pure Gaussian noise, and a denoising network that reconstructs the amplitude residuals by removing noise from pure Gaussian noise through t times iterations. During inference, given a blurry input image, we randomly sample pure Gaussian noise. After t times denoising process, the diffusion model reconstructs the amplitude residual of haze removal with Gaussian noise input and a amplitude spectrum from hazy image as condition. Finally, we feed amplitude residual to the dehazing network to achieve the dehazed result. On synthetic datasets, our method outperforms other SOTA methods with fewer parameters on SOTS indoor, SOTS outdoor, HSTS synth datasets. We also compare our visual qualities with other methods. On real-world datasets, since there is no corresponding ground truth, we employ two widely used no-reference image quality assessment metrics NIC and BRISC to evaluate the image quality. Our method outperforms other SOTA methods on HSTS real and FADLS datasets. We also compare our visual qualities with other methods. Ablation experiments regarding each component demonstrated their superiority in our method. Numerous ablation experiments have demonstrated the advantages of our method. In summary, we introduce a new perspective to handle unpaired image dehazing and propose a novel diffusion model base to fully exploit the beneficial knowledge in unpaired clear images. It is the first study to integrate a diffusion model into unpaired restoration tasks. Experimental results show its advantages. Thank you for watching.